Good morning. Let us continue our discussion on microprocessors. Now fourth part. So far we have discussed what is a microprocessor, its importance in microcomputer, how it works, and instruction set, the instructions used for writing programs, their classification based on their functionality, and how to write the program by using mnemonics, and how to convert the mnemonics into machine codes, and how to enter the program into a microprocessor trainer, and how to execute it, and how to see the results. All these things we have seen. Today let us discuss one of the important programming tools using subroutines. Using subroutines requires stack, so we also discuss stack. So today's objectives are this: using stack with stack pointer, and using subroutines. So first let us start our discussion with studying what is stack. The stack is a set of memory locations in the read-write memory. It is used to store data temporarily. It is used to store data temporarily during the execution of a program. So stack is a part of memory used for storing intermediate results or temporary data. This can be used by both programmer, and also microprocessor makes use of it while it is calling some subroutines. And next, the beginning of the stack. The beginning of the stack is defined in the program by using the instruction load immediate stack pointer 16-bit. Here 16-bit refers to the address of subroutine. Storing of data begins from stack pointer less 1 memory location and continues in reversed numerical order. Stack pointer, in stack we store data by using stack related instructions, and data will be stored from bottom to top. Hence, while taking data out, the last entered data has to be taken out first. This is called last in first out method. Next, stack is shared by programmer and microprocessor. Programmer, as and when he needs to store some of the register contents in the memory by using instructions like push, he can store them in the memory. And microprocessor also stores in the addresses whenever it executes instructions like call. Next, the programmer can store and retrieve data, the contents of a register pair, by using push and pop instructions. Similarly, the microprocessor automatically stores the contents of the program counter when a subroutine is called. Now let us see some of the stack related instructions. Whenever we use stack, first we have to initialize it by writing the top of the stack address into stack pointer. That is called stack pointer initialization. It can be done by simply loading 16-bit operand, in this case it is address, into stack pointer register. You know, stack pointer is a 16-bit register. So, this is the first instruction, LXI SP comma 16-bit. It loads stack pointer with 16-bit address. Next, push RP. This instruction is used to store register pair on stack. We can store 16-bit data on the stack at a time. We cannot store single byte of data. And next, pop RP. This instruction is used to retrieve register pair from stack, and we should remember it works with last in first out. Now let us see push RP instruction. This stores register pair on stack. RP stands for register pair. First instruction is push B, that is store BC register pair contents onto the stack. Next, push D, it stores DE register pair contents onto the stack. Next, push H, this instruction stores HL register pair contents onto the stack. And push PSW, PSW stands for program status word. It is combination of accumulator contents and flag status. Considering these as 2 bytes, these will be stored on the stack. Now let us take one instruction, push B, and see how it is executed. While execution of this push B instruction, in the first step, microprocessor decrements stack pointer by 1, that is stack pointer becomes stack pointer minus 1. Then higher order register of the specified register, in this case it is BC. So, B will be the higher order register. The contents of this higher order register will be copied into the memory location addressed by stack pointer, that is latest contents of the stack pointer. In the second step, stack pointer gets again decremented by 1, that is stack pointer becomes stack pointer minus 1. And now lower order register contents, in this case register C contents, will be copied into the memory location addressed by latest contents of stack pointer. Stack pointer, you know, holds always the top of the stack. Now let us see an example. In this program, you see, first we are initializing stack pointer with 8600. So this will be the top of the stack. Normally stack pointer will be initialized with the last memory location of read write memory area, but here for the sake of demonstration I am using 8600. Next I am taking, in the next instruction I am taking some random data 0102 into register pair BC, and then I am pushing the BC pair contents onto the stack. Let us see. First stack pointer is initialized. Here you can see stack pointer has become 8600, that is it is pointing to 8600 memory location of read write memory area. And next I am storing 0102 in BC register pair. And now stack instruction, this is push. When push B is executed, you can see first stack pointer is decremented by 1, hence stack pointer latest contents have become 85FF, and in that memory location higher order register, that is register B, contents are copied. So 85FF memory location now has 01. In the second step, stack pointer again gets decremented by 1, now it becomes 85FE, and in that memory location the lower order register, in this case register C, the contents of that register are copied. So now it has become 0 2. So now after execution of this push instruction, top of the stack has become 85FE. Now let us see how to retrieve the instruction, the data stored in the stack into any register pair. So for that we use pop instruction, pop RP. RP stands for a register pair. It can be BC pair or DE pair or HL pair. And in this case we can also pop up the program status word, that is accumulator and status of flag. Now let us consider one example, say pop B. This instruction copies the contents of top 2 memory locations of the stack into BC register pair. So this will be executed in 2 steps. In the first step, you can see the memory location contents addressed by stack pointer will be copied into lower order register, that is C. Then stack pointer gets incremented by 1. In the second step, now memory location addressed by latest contents of stack pointer, that will be copied into higher order register, that is register B. Then stack pointer contents are again incremented by 1. This completes execution of pop instruction. Let us take one example and see. So this is very similar to our previous example, except we have pop D instruction. Let us see, first stack pointer is initialized with 8600, then register BC pair is loaded with 0102, then we are pushing BC contents onto stack. You see, at the end of push B instruction, top of the stack has become 85FE. Now when pop D instruction executes, what should happen? The top of the stack contents, that is from 85FE and 85FF, these contents should be copied into DE register pair. Let us see. When pop D instruction is executed, you see, from the top of the stack the contents, that is 02, are copied into lower order register, that is in this case E. Then stack pointer gets incremented by 1. So now stack pointer contents have become 85FF. This completes first step of the pop D instruction, and in the second step it takes the top of the stack, in this case 85FF contents, that is 01, and it will be copied into higher order register, that is register D, and then stack pointer is incremented by 1. So latest contents of stack pointer at the end of pop D instruction execution will be 8600. This is how we take or we retrieve data from the stack into register pair. Now let us see subroutines. A subroutine is a group of instructions written separately from the main program to perform a function that occurs repeatedly in the main program. Normally in programs, a group of instructions will be required at many places of the program. These group of instructions are written somewhere in the read-write memory and is called a subroutine. And these instructions can be, or this sub part of the program can be called whenever required in the main program. So using subroutines saves lot of memory in the main program, because we need not write those instructions wherever required. Only we can write them at one place and we can make use of it whenever it is required. For using subroutines, there are 2 types of instructions. One is call instruction to call the subroutine, and to come back to the main program we use return instruction. First, let us see call instructions. These call instructions are of two types, unconditional call and conditional call. In unconditional call, only one instruction is there, call 16-bit. The 16-bit operand refers to address of memory address of subroutine being called. So unconditionally, that is without depending on status of flags, the program sequence will be transferred to the subroutine address. Whereas in conditional instructions, we can make use of the status of flags. Except auxiliary carry, all flags are used. For example, this CC 16-bit, you can see this is a 3-byte instruction. All call instructions are 3-byte instructions. First byte will be opcode and next 2 bytes, that is 16-bit operand, will be stored in 2 memory locations. Hence, it is a 3-byte instruction. When this CC instruction is executed, it is called call on carry. Before execution of this instruction, if carry flag is set, then when this instruction is executed, branching will take place to the specified 16-bit address, that is program execution sequence will be transferred to subroutine. If carry flag is not set, then this on carry condition becomes false, so this instruction will not be executed. In other words, the branching will not take place in the main program, it will simply go to the next instruction. And you see the next instruction, CNC 16-bit, call on no carry. When carry flag is not set before execution of this instruction, branching will take place. Otherwise, branching won't take place, program execution simply continues in the main program. This is the case with 0 flag, that is call on 0, next call on no 0. With sign flag, call on plus and call on minus. Next with parity flag, call on parity even and call on parity odd. Now let us see return instructions. While execution of the subroutine, the last instruction must be unconditional return instruction. When this return is, this is a single byte instruction, when this instruction is executed, control will be taken back to the main program. In other words, program execution of the program sequence will be transferred to the main program from where it was left. When subroutine was called, it will leave one place, so to that place it will go back unconditionally. Next, conditional return instructions. Here you can see RC stands for return on carry, next RNC return on no carry, next RZ return on 0, return on no 0, return on plus, return on minus, return on parity even and return on parity odd. These conditional return instructions can be used in the subroutine, but the last instruction of the subroutine must be unconditional return instruction. Now let us see this slide which illustrates the execution of call instruction. This is the main program stored from 8000 onwards, and when excuse me, when call instruction is executed, execution sequence will be transferred to 8050 memory location, and from there program will be executed. When return instruction is executed in the subroutine, the control will go back to the main program from where it was left, and the execution of the main program will continue. And here another call instruction has come, and when this is executed, branching will take place to subroutine 8050 and program will execute from that point onwards. And when return instruction is executed, now you see program is returned, control is returned to the main program from where it left, and execution of the program will be continued in the main program until halt instruction is seen. So we can call the subroutine any number of times in the main program. Next, let us see the format of call instruction. This is a 3-byte instruction. First byte will be operation code of call, it is CD. Next byte is lower order address of the subroutine, in this case it is 50, this 50. The next byte higher order address of the subroutine, that is 80. Now let us see how this instruction actually gets executed. Data transfer during the execution of the call instruction. You see, in the first column machine cycles are there. This call instruction has 5 machine cycles, M1, M2, M3, M4 and M5. And in the second column we have the contents of stack pointer. Since stack pointer is initialized to 8600 before execution of call instruction, its contents are like this. And next column holds address bus contents. You know, when microprocessor initiates some operation, first it has to place address on the address bus. Normally program counter contents will be placed on the address bus, and the contents from memory location, specified memory location, are fetched. And next column has program counter contents, and in the next column data bus contents, and the last column holds internal registers. These are W and Z registers. These are used by the processor when call instruction is executed. Now let us see, when call instruction is executed, the very first machine cycle is a memory read operation. We call it opcode fetch operation because opcode is read from the memory. So for that 8004 is placed on the address bus. At the same time program counter will be incremented. As response to this and control signals given to the memory places the contents of this particular memory location, that is 8004. In this case it is CD, operation code of call instruction, on the data bus, and this will be read by the processor and it will understand it. That is, it decodes. After decoding, it understands that it is a call instruction, hence it decrements stack pointer by 1. So now stack pointer contents have become 85FF. This completes first machine cycle. Now processor understands that in next 2 memory locations of the memory, address of the subroutine is present. So it initiates 2 more memory read machine cycles. So the next machine cycle is M2, second machine cycle, it is a memory read. When this is started, contents of program counter are placed on the address bus, and at the same time program counter contents are incremented by 1, and in response to this memory will place 50, that is the contents of 8005, onto the data bus, and processor will copy this 50 into its internal register Z. So this completes second machine cycle. Then third machine cycle will be started. Initially program counter contents, latest program counter contents, that is 8006, will be copied onto the address bus, and program counter will be incremented automatically by 1. And in this memory location, since 80 is there, memory will place 80 onto the data bus, and processor will read this 80 into its internal register W. So now processor has read the address of the subroutine, and before branching this branching to subroutine to the address 8050, processor here stores the latest program counter contents, which actually refers to the address of